Welcome for the third session of the day. Professor Keum will speak on Q-Homology projective planes.
Okay, thank you. Okay, I'll continue on this topic. So algebraic Montgomery-Young problem. Yesterday I just here. So this is the case of the Montgomery-Young problem where this obifold attains a complex space, complex structure, which is a normal projective surface, and each singularity is quotient singularity in this case, and cyclic singularity indeed, corresponding to a non-free orbit or exceptional orbit. So original conjecture, Montgomery-Young problem, the number of exceptional orbit is bounded by 3. So if you forget about this Montgomery-Young problem, you just think about just algebraic case, SBA Q-homology P2. So it is a normal projective surface with at worst quotient singularities and having the same Betti number as P2. And if the smooth part is simply connected, then S has at most 3 singular points. So, what if we replace this condition by this homotopy condition, by the homology condition? Well, then there are counterexamples. So there are infinitely many examples S with homology group. Smooth part has trivial homology group, but the fundamental group is not trivial. But in this case, number of singular point is 4. But this is not counterexample to original conjecture. So these examples obtained from the classification of surface quotient singularity done by Briscoe a long time ago. So let me briefly explain what is Briscoe's classification. So this is the kind of the largest non-abelian group in its list. So this is 2MRE icosahedral group, which is extension of the simple group of order 60 by a cyclic group of order 2M. So this is the center of this group. And then this group acts on C2, having the origin as the only isolated fixed point. And then the quotient is this singularity, IM type singularity. And then you can actually extend this action to the whole the P2. So here, C2 is inside P2. You just extend. And then think about the quotient. And then this one is a G-homology P2 with negative KS is ample because this is quotient of P2. So there's no torsion in first homology and minus KS is ample. And it turns out that S has 4 quotient singularities. One is coming from the origin of C2, which is a big non-cyclic singularity. And 3 cyclic singularity, 1 non-cyclic singularity of type IM, the image of the origin, and the 3 cyclic singularities of order 2, 3, 5 on the image of line at infinity. So this section, once we extend this section to P2, then it has kind of 3 fixed points. Not 3, but there are many, but the stabilizer of each has order 2 or 3 or 5. So in this case, if you throw away these 4 singular points, then the smooth part has fundamental group. It's a simple group order 60. So that the homology group should be trivial. We call these surfaces a Briscoe quotient. Well, Briscoe never mentioned about his quotient, but and how this surface look like. So it has 4 singular points. So here, IM type singularity. Well, here M can be not arbitrary integer, but there are infinitely many. There are, at M coming from kind of 8 infinite sequence of positive integers. So here, yeah, let me follow the notation, folks, like a B and 2, 1, 3, 1, 5, 1. And then you see 2, 3, 5, also the twig, each branch consists of order 2, 3, 5. And here you can choose 3, 2, the 2 choices, and 5, 1, 2, 3, 4. So there are 8 families, and here M is like 30 times B minus 2 plus some number 1. There are 8 different prime numbers. 1, 7, 11, 13, something like this, 19, 23, and 29. Actually, this 1 corresponds to something different. This is 4, and this is 2. Say. This is 3, so on. And somewhere you have, this is 3, 1. In this case, so this fork, so here it's negative B, and then the first case you have and then 3 cyclic singularities is sort of a dual. It's 3, 2, then this should be 3, 1, and 5, 4, it should be 5, 1. Yeah, and then you can easily find a -1 curve connecting the end of this. So if you contract all these things, this one first and then you get something can be contracted sigma B. Yeah, the first case. This is the case. So other cases can be also described. You have different twigs, and then sort of different cyclic singularities, but these two are always kind of the dual. This 5, 2, and then this 5, 3. Okay, so and then here's a progress. The first progress is this. Let S be a Q-homology P2 with quotient singularities, not all cyclic, and such that the smooth part is simply connected, then number of singular points is at most 3. So at least one non-cyclic singularity, then this is true. The conjecture holds. More precisely, we prove this. Let S be a Q-homology P2 with 4 or more quotient singularities, not all cyclic, at least one is non-cyclic, and such that the smooth part has trivial first integral homology. Then S is isomorphic to a Briscoe quotient. So we characterize this Briscoe quotient. And Briscoe quotient certainly doesn't satisfy this, so it's okay. So that the proof, let me give you a brief. So can I erase this, everybody? Yeah. So we should get up early tomorrow morning and then. So the idea is quite simple. There's the proof. We know the number of singular points anyway is less than 5. And if 5, then we know that the GI is the local fundamental group. Here GI is the local fundamental group at singularity pi. The order is 2, 4, 4, all cyclic. So may assume number of singular point 4. And then guys, the series reduction also coming from this BMY inequality. So BMY is Euler number of 3 minus sigma 1 minus so this means that and furthermore, condition H1 is trivial, that then these GIs are coprime, pairwise. So this leaves just a few possibilities. So it's these numbers is 2, 3, 5, and one non-cyclic singularity should have a big order. Like there are some other cases like a D8, but this is too small, and then something like the order of IM, which is 2m times 60. So this number should be bigger than equal to 1, so this is only choices. And then the idea is that the step is that these singularities are dual to the Twix of IM singularity. So well, this follows from kind of lattice theory. It's not that hard. And number 2, and then the hard part is kind of there exist -1 curves connecting one end of twig, connecting the end of twigs of the IM singularity with the cyclic singularity, with the component, with the end component. So this is the idea. So Yeah. Yeah, yeah. IM is the extension, yes. Told you. Oh. Oh. Maybe it runs too fast. How are you? Yeah, here in the Briscoe quotient here, you always have this Twix is cycling over the 2, 3, 5. So here, of course, in this case, 5, 3. In this case, you have minus 2 and minus 3. And then the other one is minus 3 and minus 2, and this is something connected, like that. Yeah. Number 2, 3, 5. Yeah. 3 we have 2 choices. 5 we have 4 choices. So there are eight families. So this number could be B can be any number, and then you have this infinite family. So the M can be any of these numbers. So, well, the situation is, so now, from the viewpoint of algebraic Montgomery-Young problem, so we don't worry about the non-cyclic case. So we may assume that every singularity is cyclic. So this is original situation coming from the Montgomery-Young problem. So this non-free orbit circulation gives us almost cyclic singularity. So here, that the Colas extension too. So this is cyclic singularity, but any quotient singularity, it should be, the statement should be like this. And more progress on algebraic Montgomery-Young problem. Now, we assume that S. Okay, now S is a Q-homology P2 with cyclic singularities only, such that the first homology is trivial, weaker than this condition. And if either is non-rational or negative KS is ample, then the conjecture holds. The non-rational case is treated in this first paper, and negative KS is ample is treated in the second paper. So under this weakened condition, H1, still it's true. And then what is the left over? What is the case left over? So it should be S is rational and KS is nef. Yeah? But this condition, and one can show that this condition also imply KS is not numerically trivial. So the only remaining case is S is rational and KS is ample. Oh, I put here, yeah. If this trivial homology, then KS cannot be numerically trivial. This also follow from kind of lattice theoretic argument. And this is the remaining case. Let now S be a Q-homology P2 satisfying two conditions. S has only cyclic singularities, and S is a rational surface with KS ample. So this is the case. But this is KS ample, but this is rational. So constructing such example is not easy. a single example is very difficult to construct. Are there such surfaces? So let's take a look. So this is the adjunction formula. S prime is the minimal resolution of S. And then this is dp. Well, this is kind of D sharp in the notation of Professor Kora's talk. And this is supported on the exceptional curves lying over the singular point P. So this is a effective Q divisor with coefficient 0 between 0 and 1. So you see here KS is ample, so this is ample. So something, the pullback of ample divisor. This is of course it's a Q divisor, value divisor. But this is rational surface. S prime is rational surface, so this is not an F. So meaning that this should be rather big, bigger than something, in some sense bigger than this. So you have to find the suitable blow up so that the blowing down curves which are kind of bigger than canonical class in some sense. So it's so that the answer is yes. And the example is given by Sean Kill and Jane McConnon and Kolla. Both they have an infinite series of examples with number of singular points too, with 2 singular points. And then with Huang, we proved that we constructed infinite series of examples with 1 singular point or 3 singular points. Which one? That's right, yeah, of course, yeah. One, there are infinite series of examples with 1 and infinite series of examples of 3, yeah? 2, of course, 2, yeah. Well, also, we interpret, Kolla's example is not coming from blow up and blow down of P2. He played with certain hypersurface in weighted projective 3-dimensional space. And then and then this hypersurface contains 2 skew lines. On each skew line, actually this 3-dimensional space, so it has 4 singularities. So each skew line passes through 2 of these singularities. So each skew line passing through 2 singularities of the surface. And this hypersurface, this surface has picard number 3. So if you contract these 2 skew lines, you get picard number 1 and 2 singularities. So we interpret his example in terms of this blow up and blow down of P2 with the suitable configuration of curves. So you pick up quite interesting union of lines and conic, or union of lines and cubic, and then you blow up in a very intriguing way, and then you will be able to contract the same number of curves as the number of blow-ups. So are there such surfaces with 4 singular points? So here I just get rid of the condition, the smooth part has trivial homology. So even without this condition, I don't know. So we don't know any example exists with 4 singularities. So in other words, are there any Q-Homology P2 which is a rational surface with KS ample and with 4 singular points, 4 cyclic singularities? Okay, so this is the status where we are. Okay, let me go on the Gorenstein case. And now let's forget about this, the Montgomery-Young problem. Let's just stick to the original classification problem of Q rational homology projective planes. These are Q-homology P2s with AD singularities. Gorenstein as Miles Reed explained, Gorenstein is almost like complete intersection. So in this case, rational double points. So let R be the singularity type. Say, for example, R is equal to A9, or 3 copies of A1 plus 2 copies of A3. And I use same notation. R be the sublattice inside the cohomology lattice. Here is the free part of the minimal resolution, second cohomology of minimal resolution, with the corresponding root lattice, where S prime is the minimal resolution of S. Since S is Gorenstein, rank R is bounded. So here is the quick proof. So 1 plus rank R is equal to second Betti number S prime. And by Nusselt formula, this is 10 minus KS prime squared. But this is Gorenstein, so there's no adjunction. So you have 10 minus KS squared. But this number is bounded by 10. So rank R is bounded by 9. So with equality, if and only if KS should be numerically trivial, if and only if S prime is an NK surface. In this case, S prime is a genuine NK surface, it's not blow up of NK surface. So with Huang and Ohashi, we have classified all possible singularity types R of Gorenstein Q-Homology P2s. There are 58 types. Here, the singularity type R of a Gorenstein Q-Homology P2 is one of the following. So 27 types and 31 types. 27 types where KS is not numerically trivial, and 31 types KS numerically. And here, so there's 27 types and 31 types. Of course, you can distinguish here, KS is ample case and KS is negative ample case. KS is negative ample case, all these 27 types appear. It's already classified by many people. But KS ample case is pretty difficult. In some cases, it does not appear. For example, single A1 cannot appear. Yeah? Yesterday, at the beginning, I told you, if it has only one A1, then it should be rational. Not so. If A1, then it should be a minus KS ample. KS cannot be ample. And also A1 plus A2, where is it? Second line. Here. Okay, so in this case also, the general type cannot happen. So the 27 types with minus KS ample were classified by Furushima and Miyanishi and Zhang. And finally, this already classified, but Ye also gave another proof. Ye was a student of Zhang. But they play with this ruled surface. They blow up and blow down and so on. But our method uses only lattice theory. So these 27 possible lattices are only possibility which can be embedded into a unimodular lattice of codimension 1. This is our. Among the 31 types with numerical trivial canonical class, 29 types are supported by NK surfaces with finite automorphism group. These are except this 2 red color, 29 of them. But NK surfaces with finite automorphism group must have finitely many -2 curves and were classified by Nicolin and Kondo into 7 families. 2 of them are one-dimensional and 5 of them are zero-dimensional. General NK surface has infinite automorphism group. So these NK surfaces are rather special NK surfaces among the 10-dimensional moduli of NK surfaces. And for each of the 31 types, recently Marta Schwett just has constructed a explicit one-dimensional family of NK surfaces. Well, this dimension 1, this is maximum possible. So I'll show you briefly. So all these 31 types, each of these 31 types, there are moduli space of one-dimensional, I mean, there are one-dimensional moduli space. And such one-dimensional families can also be obtained by Q-Gorenstein smoothing technique formulated by Colline Shepard Baron and used by Yongnam Lee and Jong-Il Park, which was useful to construct a new simply connected surface of general type with PG0. Well, we haven't been successful for all these 31 types, but except a few that we're still working on. Here, let me brief review the moduli space of NK surfaces. Here, let currently MR, M sub R, is the moduli space of NK surfaces with fixed AD configuration R, meaning that this moduli space of NK surfaces with smooth rational curves with the Dinkin diagram R. And let X be such an NK surface, then rank R is bounded by 9. On the K3 cover, each minus 2 curve split into 2 minus 2 curves, E plus and E minus. So Y contains, the K3 cover Y contains 2 copies of the AD configuration. And Picard group of Y, Picard lattice in this case, K3. In this case, this one contains the pullback of Picard lattice of X and R prime. This is generated by the difference between the two. And the addition, E plus, E minus is contained here already. So they are also on R. So here, this one is rank 10, and this is rank R prime, same as rank R. So this one has rank 10 plus rank R. So such K3 surface must have a Picard number at least 10 plus rank R. So such lattice polarized K3 surfaces, meaning that say K3 surface whose Picard group contains a fixed lattice. From a moduli space of dimension 20 is the moduli space of all K3, including non-algebraic, or Keller K3. So subtract the rank of this. This is 10 minus rank R. So such K3 surface has moduli space of dimension at most 10 minus rank R, so that the dimension of this corresponding moduli space of NK surfaces has the same bound. So if R is 0, then we have total moduli space for all NK surfaces. If R is just A1, this means that the NK surfaces with at least one smooth rational curve called nodal NK surfaces. In this case, this is dimension 9. We know that this is bounded by 9, but actually this is 9. But for example, 9A1, this is rank 9. So the dimension is at most 1, but actually this is empty. Yeah? If there are 9 such, if there is such an NK surface, then you can contract to 9 singularities, which is already violated. We proved that here, number of singular points is at most 5. There's no such thing exists. So what Xue's recent result says is this. If this is non-empty, I mean here, if this rank is equal to 9, and if this is non-empty, then the moduli space always one-dimensional. And his proof is more constructive. Actually, he constructed all moduli spaces, all components of the moduli space. Well, his idea is using elliptic fibration, and also it's Jacobian, which is a rational elliptic surface. And especially in this case, all these minus 2 curves we have too many minus 2 curves. So this elliptic fibration should be extremal. I mean, the singular fibers are kind of most reducible. It has plenty of components. So in other words, in general, this 9, if you assume that rank R equal 9, then 8 of the 9 curves should belong to a singular fiber, the union of singular fibers of a certain elliptic fibration. Okay, so, well, symplectic case, I don't say much. The original Montgomery-Young problem, I repeat the question of Janos. Are there topological homology inequality? Something like this. The obifold homology inequality holds for symplectic Q-homology P2. It's a symplectic for manifold. Well, for symplectic manifold or any differential manifold, we don't have the notion of nephness or something. So in positive characteristic, so also you can also define, so this is now in algebraic geometry, a normal projective surface S is called a Betti P2 if it has same Betti number as P2. So here I use, here in positive characteristic, the singular homology or singular homology doesn't make sense, and singular cohomology doesn't give us much information as a sheep homology. So here, but we have a nice cohomology theory in positive characteristic, L-logic cohomology in atal topology or crystalline topology, crystalline cohomology. So anyway, if L is not equal to the characteristic of the field, then this gives us expected Betti numbers. So this 0 and second Betti number 1. So in this case, I don't call Q-homology because in positive characteristic, Q-homology doesn't make much sense. If S is smooth, then it's still we have S is P2 or fake project plane. This is canonical class negative ample, and this is canonical class ample. Well, in positive characteristic fake project planes, nothing has been known. And over complex numbers, we know they are Ball quotient, but in positive characteristic, we don't have such description. And suppose we have a fake project plane over complex number in characteristic 0, which is defined over some number field or Q, for example. Then maybe you can have reduction mod P, get fake project plane in positive characteristic. But here also, here's one comment in positive characteristic. BMI inequality does not hold in positive characteristic. Here's the one interesting counterexample, Mukai. In positive characteristic, there is a projective surface with canonical class ample, and second Chan class is negative. Yeah. So over the complex number field, in this case, this number is bigger than or equal to k squared. But this is negative. Okay, but anyway, in characteristic 2, so this bound does not hold. In characteristic 2, there are Betti P2 with more than 5 rational double points. I found this paper last night. Here is the interesting example. There is a configuration of 7 lines in P2 with 7 triple points. This is so-called 7-3 configuration on the Fano plane. So this is a plane over the field of 2 elements in characteristic 2. So this plane consists of 7 points and seven lines. And each point lie on exactly 3 lines, and each line passes through exactly 3 points. So you blow up all these 7 points so that the proper transforms of the 7 lines are -2 curves pairwise disjoint. And then you contract these 7 minus 2 curves to get the Betty P2 with the 7A1 singularities. Well, this one violates this, but somehow you see in characteristic 2, this A1 singularity is not quotient singularity. So you see, in characteristic 2, this singularity is not a quotient of something. It's not coming from quotient. So the order 2 action in characteristic 2 is a wild action. So maybe still we have some hope, certain restriction. Maybe still we have some BMI inequality in positive characteristic, yeah, with under the quotient singularities. Well, you can have such a similar construction in any characteristic P, and over the field of FQ. And this one has this configuration. So this one has 1 plus Q square points and lines. And then you do the same thing. And then you have minus Q curves, 1 plus Q square. And again, this minus Q curve is not a quotient singularity, but still you have a Betty P2. So in this way, you can get a Betty P2 with arbitrarily many. So there is no bound in this case. Okay, I'll stop here. I finished a bit earlier. Good.
Any questions? If not, let's thank the speaker again.
Okay, thank you.